All right, we have enough of us here. This is a geology class originally, and we have enough people who actually are thinking about mineral reactions that I wanted to talk about how to solve for mineral reactions. And this is also just to remind you, even if you aren't interested in mineral reactions, right? That we've been solving one kind of equation and one kind of system of equations. And this is just to remind us all that there are other systems of equations and other ways of solving. Um, we're talking about kinetic reactions, and that's what the previous lecture was, where we had talked all about first order reactions, first order kinetics, and we'd gotten into some ways you could describe biodegradation and reactions like that. And now to talk about our kinetic reactions with water-rock interactions, we need to review equilibrium chemistry first. So a quick reminder, if you have an equation for a chemical reaction where the lowercase are the coefficients, the stoichiometric coefficients, I hope this is coming back to you, right? And these are the concentrations of different constituents, all right? Reactants, products, all right, chemistry. All right, the equilibrium constant, K, is the concentration taken to the power of its stoichiometric coefficient. All right. And the reactants go on the top. Oh, sorry. The products go on the top and the reactants go on the bottom. So I just want to point out, we won't do this too much, but I want to point out that this can be written this way. All right. This is like a summation where you add a whole bunch of terms. Instead, this is one where you multiply each term. So I equals 1 to start with, and you figure out what this is, and then you multiply it times whatever I is 2. So if here is I is 1, I is 2, and these coefficients, these stoichiometric coefficients, that's what this is, the stoichiometric, here we say, stoichiometric coefficient, right? So for reactants, these stoichiometric coefficients are negative, and for products, they're positive. So multiplying all these things together is exactly the same as this. All right, and we're going through exactly how many things there would be. Here we have 4 of them, so I would be 4. All right, you just multiply them all together. Okay, so that's equilibrium chemistry, and this is how we write that in shorthand instead of having to write out the whole equation each time. All right, now I promised kinetics, and so I want to give you an example of a kinetic reaction. And this one is plagioclase dissolution. And you see here there's some kind of reaction rate. What's X? X is the remaining volume fraction of plagioclase. Okay, so it's how much there is. All right, and it equals minus K, which is the kinetic rate constant, times how much plagioclase there currently is. All right, because if there's a lot of plagioclase, there's a lot that can react. And if there's very little plagioclase, there's not going to be you just can't change the fraction of plagioclase very much, right? And N is an empirical constant. All right, so the way you get this is you look at a bunch of rock samples and think about how much plagioclase there is at each depth. All right, and then you can fit that to time if you know how fast these things are buried. Keep in mind, though, that the rate constant is a function of temperature. So, and here's where the temperature fits into it. All right, it says that the kinetic rate constant is some empirical factor times e to the, and this is the activation energy, R is the natural gas constant, and T is the temperature, and remember, it's always written in Kelvin. All right, because your natural gas constant is also Kelvin. Okay, Kelvin, Kelvin. So as the temperature goes up, the rate constant actually also goes up. All right, because this is e to the minus. So you can work that one out. All right, so this is a very famous example of a kinetic equation. I think I've told you already in this class that there's a famous paper called, well, I don't know how famous it is, but there is a paper whose title I enjoy very much. It's Absolute Failure to Precipitate Dolomite in the Lab at Room Temperature Over 30 Years, right? Dolomite. Nobody can reproduce it at low temperatures, and yet we observe dolomite around the world that appears to have formed at reasonably low temperatures. Once you get to 100 degrees, equilibrium, it goes fast, it's easy. But temperatures lower than 100 degrees, it's slow, and this has created a huge, long-standing mystery about how did all the dolomite get there. And so, of course, people have tried to measure the rate of dolomite precipitation. All right, so it doesn't happen at equilibrium. It happens very slowly. Can we describe a rate constant for it? All right, and so this one has our reaction rate equals, now this time, and I'm going to warn you, in this series of lectures, we're going to be reusing letters like crazy. So in general, I've just repeated them every single time, so you don't try to remember what they were. I mean, these are going to be constant. We're going to use Q and K over and over again. But these other ones are going to get reused a lot. Okay, so at this point, R is still the reaction rate. That's a constant. The number changes, but the fact that R is a kinetic rate constant is what is consistent here. This is the specific surface area of, it's supposed to say dolomite. This is basically how much surface area is available to react. All right, you can imagine if there's a lot, the reaction rate will be faster. Now, where we've seen the equilibrium constant, I want to introduce the activity quotient. All right, K is you multiply the concentrations of things together, and if it's at equilibrium, you get K. If you multiply the concentrations of things together and it's not at equilibrium, what you get is this Q. All right, so that's what we mean by activity quotient. We multiplied all the concentrations together and it didn't equal K. What it equaled was Q. And I had forgotten that we talked about activities this early in here. Once you get to non-dilute solutions, the things that go in the equilibrium equation are activities, not concentrations. Think of them as concentrations. They're slightly modified, but think of them as concentrations. All right. And as before, this rate constant is temperature dependent. This is the same equation. This one recurs quite a lot. And you see here, I've just written this the way we did the equilibrium coefficient before. So this is, in theory, a non-hideous example. Let me point out this term, though, and let's think about this. This is, if you're actually at equilibrium, then Q equals K. So this is 1 minus 1 is 0. It says that if you're at equilibrium, then the rate constant is 0, because you're at equilibrium. We know that they're always at equilibrium. Some of the reaction is going forward, some of it's going backward, and those rates are in balance. All right, so we make this net rate be 0. All right. If the, and this is an empirical coefficient, and so you can see the farther out of equilibrium you get, the faster this reaction will proceed. All right, and so this is done just kind of empirically. Okay, so now you've seen at least a famous example of an empirical kinetic rate expression. And what I want to show you now is just a general version of that, because they can definitely get a lot worse. And there is still a general formulation. All right, so to remind you that our reaction rate here for the mineral K, we're fixing this, so this is getting very general, the mineral K, and you'll see it appears in all these guys. All right. And just a reminder that this is sort of the change in concentration of something, the mineral, it may be some aqueous constituent whose concentration is changing. So this relates to a change in concentration with time. All right, so you see some familiar components of this equation. They're subscripted K because there could be K kinetic reactions. All right, but you've seen this term before. We're going to see now that it's called the mineral saturation index. And let's just think about it for a minute. Oh, we already thought about it for a minute. That's right. So you already know that when this is at equilibrium, it's 0, and it doesn't matter what anything else is. The reaction rate goes to 0. And when when Q is very different from K, then this gets to be a much bigger number, as big as 1. And that scales this whole thing. So a faster reaction rate then. All right. This is the porosity, so we can kind of work with that. And these guys are hopefully familiar at this point. A is the reactive surface area, A for area. And we talked about that the more reactive surface area there is, the faster the reaction will go. And K, again, is the kinetic rate constant, which yet again is a function of temperature. We have this equation one more time to keep us reminded of what that is. All right, so these things we have kind of seen in the previous equations. This is the new term. And so let me read you the remaining bit for it. This is the concentration of some constituent, I, and this, where we would, this looks like the activity quotient. It looks like Q, right, where you multiply a bunch of things together. All right, but this P sub ik, which is the coefficient that pertains to the ith constituent in this term for the kth mineral. This turns out, we would think this would be the stoichiometric coefficient, but this term is a get out of jail free card. You certainly could have individual constituents that appear in your stoichiometric equation. You could have these in here, and P sub ik could be that stoichiometric coefficient from that reaction. But this term can also be used where you just have empirical evidence that some other constituent affects the reaction rate. There's some reactions for which having sulfide around, even though sulfide isn't mentioned at all in the stoichiometric equation, somehow it affects the rate coefficient. All right, we know that we should probably find out why, but for now we have empirical evidence. So we could put sulfide in. This I goes from 1 to n, and you can put whatever you want in there, okay? And by that same token, there's no stoichiometric coefficient for, say, sulfide in your stoichiometric equation. So this is an empirical thing. Okay, so it's not a very pretty equation. It's still this is very empirical. Trying to decide what the reactive surface area is very difficult. A lot of reaction rates are calculated in the lab using powdered and cleaned samples, and both of those things make what you're experimenting on pretty much entirely unlike what you'd be reacting in real life. So it can be very difficult to decide what to do with it.